Hello everyone, welcome back to our next lesson. This lesson begins on page 12 in your notes, and it's called Reading Ordered Pairs and Verifying. What they're trying to get you to do here is look at a graph and look at the equation of some function and determine if that graph and that function are one and the same. For example, if you look right here, here's an example number 9. We'll do this one now in just a moment. I can clearly see a parabola, that nice red parabola there, and I can clearly see a function right here. So the question is that graph the graph of that function? Now, I suppose one way you could easily do this would be to just take the function and graph it manually or using a website such as desmos.com, beautiful website for drawing graphs, or using a graphing calculator, and see if the graph is exactly the same as the one that's given. But that's not what they want you to do here. What you're going to do here is look at your graph very, very carefully, and you're going to pick some points on that graph. For example, if you look right here very carefully, you see that point right there? It appears to me that that is the point 5, 5. All right, x is 5 and y is 5. Now, if that given function really is that graph, if it's really the same thing, then if you were to put 5 in for x into your function, you should get back 5 for your y value. Because remember, every point on the graph of a function is a solution to that function, a solution to its equation. So we're going to put this point right here, say 5, 5, into our function and see if it actually gives you back a 5. But the question is, one point is not enough. One is not going to do it. How many points should we plug in from that graph into the function to determine if they really are one and the same? And the answer to that question is you always pick one more point than the degree of the function you're testing. So if you look carefully at this function right there, you can clearly see it's quadratic. Degree 2, x squared is the biggest power of x in the function itself. So if you take that degree 2 and add 1 to it, you get 3. So in this case, we will need to test 3 points. Now the points you pick, you'd better be very, very accurate with them. Those points should be exactly on locations where grid marks cross, because you want exact coordinates, not approximate coordinates, all right? You have to get them dead on. They have to be exactly correct. So 5, 5 is 1. That looks like a good point to pick. We can pick that one. Now look at your graph very carefully. Can you pick out some other points that are exactly where grid marks cross? And it takes a keen eye sometimes to actually pick out points that are there. Let me see. How about if you look carefully right here? You see that point right there? That, to my old eye, looks like 3 and -1. All right, so we can use that as our second point, for example, to test. And let me see. Oh, and what about the vertex? Look at that. The vertex is 1, -3. Okay, so we can use that as our third point to test into our function. Now, if even one of those points proves to be false, if I plug in, say, x equals 5 and get back something different than 5 for y, then that means the function and the graph are not one and the same. The given function does not represent the graph. And that's why they tell us in the example here, because it's quadratic, we have to get 3 ordered pairs on the graph and then plug them in. Now there's other points there, by the way, you could have picked. This point right here, for example, looks to my eye like -1, -1. Let me see. Let me go along the graph. Here's another point you could have picked probably. That would be -3 and 5. Any of those points would work. You don't need to test all 5. Just test 3 of them. So here we go. So one at a time. Now I'm not going to show the actual calculations. I'm assuming you all know how to put an x value into a function and work out the y value. I mean, you could even just use calculators if you wanted to. So let's try plugging in 5 for x, okay? And we're testing this point right here now. We're testing that point right there. So if you plug this in, you're going to have 1/2 times 5 squared minus, and then 5 again in for the other x, minus 2.5. All right, now you plug all of that into your calculator and carefully work it out. And I'll just tell you what you're going to get back. You actually get back 5. Well, that's great. That's great. That means that the point 5, 5 is on our graph. It is really on the graph of that function. So this first point tests out perfectly. That's great. Good news so far. Now, by the way, if I never got back a 5 there, then you don't need to test any other points because you know the graph and the function are not one and the same. So let's check another point. Why don't we try the 3 here now, because we identified that 3, and we're hoping to get back -1. That's what we're hoping to get back. So you plug this in again and blah, 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 1/2 times 3 squared minus 3 minus 2.5. So you type all of that into your calculator carefully. And if you do so and work it out, look at what happens. Bam, -1. You do get back the expected y value. So that point right there seems to justify saying that the function and the graph are one and the same. But it's still not enough. We must test one more point. If it was a straight line, by the way, you'd only have to test 2 points, because a straight line, a linear function, is a degree 1 equation. So add 1 to degree 1, you get 2 points to test. If it was a cubic function, you'd have to test 4 points. All right, well, what do you want to do now? How about the 1, f of 1? All right, that's where the vertex is located. Now, this is the final point we need to test. If we get back -3 by plugging in a 1 into that function, then we know for absolute certainty that the graph and the function are one and the same. So you would have 1/2 times 1 squared minus 1 minus 2.5, and you plug it in, and guess what? -3. Just what you were hoping for, just what you were expecting to get, or what you wanted to get. So anyway, we've tested 3 points. All 3 points turned out to be solutions to the equation, and because of that, now we can say beyond a shadow of a doubt is that the graph, this graph shown, does represent, or it's the same thing as, if you wanted to say that. This old pen is not working very well. It does represent the function f of x. You could even write down what the function is if you wanted to, but that answers the question right there. Okay, so that's that one. That was example number 9. Now again, that was on page 12. I'd like for you now to try the practice questions on the bottom of page 12, right here. Again, this is another quadratic, so you're going to need to test 3 points. On top of page 13, it's another quadratic. So again, you have to test 3 points. Now make sure, be very careful about the points you pick. They have to be right on grid marks. You want to get them exactly. And the last one there is C. Now, by golly, that one is a little tricky. All right, it is quadratic again. So again, you need to test 3 points. But you better look at that. Notice the scaling of the graph. All right, they've actually got, if this is a, wow, okay, there's 0, 0 right there. There's your origin. So they've got 10 blocks going over here to 2. Well, that means that 5 blocks, there's your 1. All right, so every block represents 0.2. Be very careful of the point you pick there. Here's one good one. I can see that, obviously, right away. 0, 2 would be a good one to test. And now look at your graph carefully. You have to get the points exactly from where grid marks cross, okay? So anyway, I'll leave those for you to try. And if you have any difficulties with them, pop me off an email. Check your solutions with D2L. And I'll end off there with this video, okay? Bye-bye.